they will see it.
So it's like a screen?
Yeah,
copy
the
or-
screen is going to be something that is, so it's going to look like, I will show it to you momentarily. So it's going to be looking like, going to put this presentation mode like this. This needs to be put at bigger. So there's an email that comes to me. Okay, this is live here. This is how it looks at the moment. You see that I'm here in the
Oh,
corner.
that's cool. Uh-huh.
You're there too, so that's why the green screen.
Yeah.
Yeah.
The
So-
green screen is much bigger than.
Oh, so I need to adjust this one a bit.
Now I can see this. How does this work?
It works pretty easily, so like this. Then it's good to go. And then we just put the, it's already streaming, so
There's a time delay.
a few seconds, yes, a few seconds.
There's really a time delay. Now
But
it's-
you can get rid of that if you're not happy with it. So you can use you can simply say that there's like 1 second time delay. Then you need to compromise the streaming quality a little bit.
Yeah,
But this is how it look. So let me see if everything on it. So I think I still need to put a little bit of smaller. So the OBS is the way to go.
Yeah.
OBS.
Yeah, I have used OBS for all my videos, by the way.
Oh, nice.
Yeah, but I never streamed them. So we recorded them, and that's
Ah.
it. Yeah.
Okay. Like this is the way to go. Okay. So then, so let me see. So most of the participants going to be online participants, and there's already 11 persons online.
Okay. And will there be anybody here as well? I mean, these are also students, or?
Yeah.
Yeah.
Oh yeah. We need one more thing we need to do.
Can you try
Yeah. This one.
HDMI? Yes. Would you have to bring these down?
What number? This is. Oh, again, it changed a little bit of how things look like. Yeah.
Oh my God, this is like surround.
Yeah. I don't know why they do it. I'm not a big fan of
I'm
this.
not tall enough to do that, so
Okay,
you're
so-
the tallest person. Can you bring those down?
Yeah. I can. Just to see how are the.
There is no button for them, and you have to grab them from the top.
Maybe with that one.
I can make it happen.
But you have this thing that I would like to have at every lecture room in Innsbruck, yeah?
You
and
can take
have
it, nobody
here,
is going to
but
notice.
yeah, that's the point. I mean, you just can, badly treat people with that.
Exactly.
But
Absolutely.
maybe it's
why
the idea.
we need it, but exactly.
Okay, if we sit here.
Discipline students,
That's the way.
Yeah, it
No.
has pretty nice leverage, yeah.
Oh my God.
He is. Other than that, I would be afraid.
So you're thinking I can do the math about the risks? This is moving no risk. Okay. Okay, still I want to make my final assessment about how you appear. So, Johannes, you used to stand roughly here from the camera.
Stand, yes. Okay.
Yeah, because you need to be able to see this guy, this camera.
Okay. And you will say some introductory words, or
Yeah, I can do that.
I'm not sure. It's up to you. Okay.
All right, so we are almost ready to go. So we just need to wait
Are
another.
you going to be in screen as well, or is it just Johannes?
just Johannes.
So Jonas, can you come so that I can adjust the height of it? So let me check. It's, I believe it's perfect.
Looks perfect.
I don't need to touch it.
Looks perfect. And later you can take a look at how is your lecture. This is going to be recorded. Of course.
Ah, okay, I can look at. Yeah, yeah,
Stream
yeah,
it and
yeah,
it's
yeah.
going to be available on YouTube.
Oh, that's good. Yeah. You know, the point is that I even didn't look at any of my lectures because there's so many hundreds of hours. So the, yeah.
Because you change the meeting time tomorrow, but I have to travel. It's a bit difficult.
Yeah, because you're living already tomorrow.
I know
It
that
should be then just skip it and communicate via emails if there's anything you need to be communicated.
Yes, if it's okay by you.
Yeah, that would be fine to me. Fine to me, but it's just it's a little difficult day to me too because I want to make my life ready before heading on.
Yeah, I
on-
understand.
on
That's the
Wednesday.
reason why I asked you that can we meet on Monday?
Yeah,
I know
yeah,
that's a bit of
and
a
I forget it.
situation.
I completely forgot that. Forgot that. Okay, guys. Okay, so there's more guys coming in. All right, so we're good to get started. Respect. Respect. All right, so what's happening today is going to be two things. First of all, we will have a visiting lecture coming from all the way down from Austria, from Innsbruck. And this visiting lecture is going to be a doctor, Professor Johannes Gersmeyer, good friend of mine. So I met Johannes already more than 100 years back, and we've been working together in a multiple different projects. And we're going to learn something that I feel is going to be a fun thing to learn. It's called Exodine. It's an open source software that is a little similar than Chrono. Remember, there was last year there was a visiting lecture about the Chrono. That was an open source software like it is Exodine too. Then once done with Johannes' lecture, then it's going to be the summary, what you guys needed, what you need to know in midterm exam. Because midterm exam will be on starting from next week. And regarding the midterm exam, I made several podcasts using Notebook LM. Those podcasts will be available in Finnish language and also in English language. And I asked Notebook LM particularly to answer the questions that are available in that are in a selection of this question bank. So just follow the podcast, and it's going to be one way to get started in your preparation of midterm exam. But without further ado, so let me introduce you, Johannes. Johannes' lecture is going to take roughly
90 minutes, I said?
90 minutes.
80 minutes maybe, because it's 90 minutes slot. Is it okay?
Yeah, that's fine.
Yeah,
That's
yeah,
fine.
yeah, okay.
But then it's going to be very short introduction about what you guys need to know in midterm exam.
Yeah, I can make it short if you like. But,
You can make it a little bit shorter, so
Okay.
we have a little bit of time to discuss about what's up in midterm exam.
okay, okay.
Okay, enjoy.
Okay, so good morning or hello from my side. My name is Johannes Gersmeyer. I'm from the University of Innsbruck, and it's my pleasure here to give you an introduction on our simulation engine. And it's not about only the engine itself. It should encourage you to not only work with it, but to understand the concepts behind it. How could you program smaller or larger codes, not only in multi-body dynamics, but also in other areas. So this is the idea to present it here, to see how did we do that, how could you do similar things, and what are lessons learned maybe that you should avoid, and things like that. That's what I want to show. And of course, I also want to show how we are dealing with the flexible multi-body dynamics simulation. So really, I'm happy to be here today, and I just have, and if there's any questions, please just ask and interrupt me. It's no problem. I can just not follow the YouTube stream, but if there's anything, my people here
I will follow
will.
the stream, so I will let you know if there's any comments from one of the participants.
Yeah, okay. I
Right
keep,
now, for your information, there's 17 persons following.
that's good. That's good. It's really a pleasure, and it's the first time to streaming to YouTube for me, so it's so I'm quite excited about it.
You can be like rich and famous just like that.
Yeah. Okay, so some contents not in the correct order maybe, but it's like, so first is the structure and background information. The second thing is the concepts behind it. Then it's what I'm talking about then is a C++ package, but there are some extensions in Python, and I will explain how we deal with that. I will also show how we combine Python with C++ in that regime, and I will show some advanced things like parallelization, flexible bodies, and contact. And the whole thing, as you might read in the bottom line, it's from the Exodyne workshop. I was actually expecting to deliver this here, not to the students, but I thought it's like a regular talk, so I wasn't sure the audience is about, but yeah, that's how it is. I will also show examples, and I wanted to show actually an online example, but this is, I think, not so easily possible because Aki didn't install Exodyne, I think, so that's why I cannot show it. But you see a lot of videos here on this slide. These are typical examples that we are doing with Exodyne in very different areas, very simple mechanisms, also with particles, machines, bearings. Robotics is a big field because we are using Exodyne also as a robotics engine in teaching, especially, and also for research. Mostly we are using our code to develop new models, new methods in multi-body dynamics, and this is what I'm going to talk about. Yeah, the motivation that I always say why we are developing still a multi-body code, the motivation is basically, as it is written here, the systems become more complex. Yeah? When we started 20 years ago, you could develop a simple plate or beam, and then the beam was moving, and you were a hero. Yeah? When your beam was animated, and you showed the dynamics of a beam, you were a superhero, and you could become professor, right? But now it's different, and the question is, how could you achieve that? And my argument is that if you want to deal with complex systems, you cannot develop every component by yourself because you just still have 3 years for your PhD, or our PhDs have still 3 years.
I need to make a
Yeah.
minor
Oh.
adjustment because
Yeah,
we
okay.
got the complaint that audio is only on the left side. So let me
Oh.
see. So this needs to be lifted maybe because for some reason it needs to be.
Okay.
So I think it's going to be better like that.
Okay. Is it? Let's see if it's better.
The online people will complain if not.
Ah, that's good. That's good. And please also, the on-site people, if anything goes wrong, just let me know. Yeah, so this is the main motivation, to have a code that supports people to develop specific methods, but not having the need to develop everything to get this done, like to model a robot or a bearing. So you can just work on your component that you want to develop. And this is the idea, basically, of the simulation environment Exodyne. It was initiated in 2019, and this could show that it is not a very big effort to get something like that done, because the development took like 3 years, for me at least. Why? Because I had already developed an earlier package, and it was not just copied, but it was really designed completely from scratch. Yeah, it was practically nothing copied from the old code, but knowing, of course, what to do and how to do it. So it's a quite young code, let's say, this way. And the basic idea was in this design to make it efficient. Yeah? This is also written here, like there is the performance requirement that you could simulate it with small systems. You can do millions of time steps per second. This is a requirement that you sometimes need, that you have a very simple system and you just want to simulate a simple system fast, as you can do it sometimes also in MATLAB or Python with a simple ODE, and you can integrate it with ODE 4.5. But sometimes we have large systems, as you see on the right side, this engine that we use as an example. It has like usually a couple of 100,000 of degrees of freedom, and if you have more than 100,000 of unknowns, you need to use special solvers, and then you have to switch your solvers to a completely different set. You have to use sparse matrices, and to integrate the two things is a very, to my understanding, an important requirement. So this was the basic setup. Now, if you work in C++ with solvers, numerics, and so it gets painful, and this is something that has to be done by experts, and that's why I say, okay, only a few people work on these solvers, and the others could just use them to do their work. Yeah? And the second thing is that if you want to integrate complicated multi-body models, then it's not the best way to do this in C++. You would, I think C++ is a very bad coding language when it comes to developing fast, complicated mechanical models. Yeah? C++ is really difficult to work with. You need a lot of base classes, and you can do a lot wrong. Yeah? That's also maybe a thing, that you can do so many errors. And what I did in the first code 20 years ago that I programmed, I did a lot of error searching, searching for errors a day or 2 days. Yeah? And this is what you should just avoid. That's why my recommendation not to use C++ or only to use it where it's necessary. And this is actually the idea here in Exodyne, that we have a Python package that is doing most things except for that what you cannot avoid, what has to be done in C++. This is more or less the split up. So let's say like here, if you have the creation of models or user functions or complicated objects, some high-level operations, interacting with the simulation, everything that you don't have to do in C++ is done in Python. And in Python, everything becomes much easier. But I'm not sure how many Python users are here in the lecture room. Who is using Python? Okay, and who is using MATLAB? MATLAB, yeah, so, okay, still a lot, I see. Of course, you can also do this in MATLAB, but it's more complicated. I think in Python, the interaction with C++ works easily because it's an open language. It's fully open, and many projects use this technology. I mean, all the AI projects use this interrelation of C++ and Python, and that's why it's really designed to be used like that. We didn't know that AI will have the breakthrough now, some years ago. When we designed Exodyne in 2017 or 18, we just switched to Python by good luck, I would say. Yeah? We didn't know about the development of Python, but now we see, looking back in time, that this was the right decision. I don't know what would be the best decision for the next 5 or 10 years, but I still think that Python is a good way to go. Okay, but what I want to say here is, if you develop a project for simulation, doing some simulation, it is really very efficient to think about which engines to use and to combine. And I think this is a good way to start with. Okay, I will show about these Python models later on. There's also a lot of documentation in Exodyne, and I don't want to make advertisement for that. But again, how do we do that documentation? It's fully automatic generated, or let's say 80% is for sure automatically generated. This is what we learned from the old projects. You should not, how to say, when you think about documentation, you need documentation. I mean, otherwise your code dies within short time. So you need documentation. You need to document every method, every parameter, every switch, whatever you have in your code, and these are thousands of parameters that you would have in the end, and you have to document them, right? Now the question is where to document them. In the C++ code, in the Python interface, in the Python description. There are many places where your parameters appear. Yeah? Usually if you have interfaces, then you have the C++ side, you have the Python side, you have the interface, you have user documentation, you have an online documentation. So where to put the documentation, right? And the most important thing is, to my understanding, just to have the documentation in one place, and this place is then spreading to all the other places, so you have one consistent documentation of everything. Yeah? This was a basic idea to start with. We did not start it in the best way, I would say, but what I learned also from Google is sometimes you just have to use code generation engines. You have to create an ecosystem where you define documentation and parameters, and from that you generate the code and documentation. And this is all automatically generated, as I will talk later about. Okay? And maybe also to mention here that so everything that is included in Exodyne is quite standard, I would say. Not totally everything, but many things are really standard. But the new things that we are developing, they wouldn't be possible to develop without this code. So it's like you need to have a code to develop new things. That's what I want to say with that. So Exodyne is really our workhorse here, and it's also very heavily used in teaching. That's why we like that. Okay. Now we go to this background, what's inside. It's a redundant multibody formalism that is basically integrated into Exodyne. It's even more than that, because you can model multibody systems, but you can model any other system that is consisting of algebraic equations, differential equations, first order or second order differential equations. There's no stochastic processes, by the way, so there would be an extension to more general systems. You cannot do quantum physics or whatever in Exodyne. This would be a very heavy extension, but what you need in mechanical or mechatronics engineering would be included here, basically. From the multibody side, it's a redundant multibody formalism, which means it, in the end, usually gives you differential algebraic equations. I'm not sure if this is already well known to everybody. It means that you have a mixture of differential equations and algebraic equations. Yeah? And it sounds like, okay, we are mixing them, but the problem is that there's only very few solvers that can deal with these differential algebraic equations. So if you have algebraic equations, then you usually use some direct or sparse solvers. They are standard in every numerical package. If you have differential equations, there are hundreds of packages that can solve differential equations, like ODE 4.5 that you use usually in MATLAB or Python, and many other integrators. I would say there's hundreds of different integrators that you can use. Usually most people use the same one. In differential algebraic equations, there is not a single solver that you would say this is the standard one, the best one that you can use. Yeah? Because every currently existing integrator for DAEs is still having problems, and that's why most people avoid redundant multibody formalisms. Yeah? It's a very simple explanation for that. So when you want to deal with redundant multibody systems, you first have to develop a solver, and this is what I did 25 years ago. That's why I'm quite convenient with that. What solvers can you use? You can use specific implicit methods, but nowadays we use the generalized alpha method, which is now well established, and it works well, but it still has problems, just to mention it here. The redundant multibody formalism then consists of several components. The main components here are, as I named it here, nodes, bodies, markers, and constraints. There will be more explanation later on, but basically our bodies, rigid body, flexible bodies, they are built upon nodes that provide the unknowns, and then they are connected via marker interfaces that provide the interfaces for the constraints and loads. Yeah, so basically there are rigid and flexible bodies, as I said already, implicit time integration. If we don't have DAEs, that's also important. DAEs require special solvers. These special solvers are efficient, but not very efficient. So there are more efficient methods if you use explicit time integration. And that means now in Exodyne you can always switch. If you have only differential equations, no algebraic equations, then you can use explicit solvers, and they are more efficient for like robotics, for example, or contact. And this is done with this embedded kinematic tree. So like the robot here you see on the right side is modeled with a kinematic tree. Kinematic tree means that this is a recursive formulation, more or less, as standard in robotics. And this recursive formulation then uses minimal coordinates, and these minimal coordinates then allow you to use explicit time integration, and this is more efficient in robotics or contact. Okay, and you can mix it, and the nice thing is, if you now want to close a loop with the robot, so that you say, okay, the robot should touch another robot, and you close a loop with a constraint, then you wouldn't have an explicit, or you wouldn't have a minimal coordinate formulation. It's then redundant, but then you can just switch the solver to implicit solver. Yeah? That's very easy, that you don't have to completely start from scratch, but you can just switch the solver. Okay. Then this slide should show how a model is built more or less in Exodyne. It's a graph showing a typical model. It has a, I'm not sure if there's more. So there are nodes. The nodes are shown here in red. There are two rigid body nodes that you might see from here. The abbreviations is like a node rigid body node, like for rigid body or other, like for a beam you would use two rigid body nodes, for example. And EP means Euler parameters that are used for these rigid body nodes. And then the objects are based on these nodes. So you have two objects here, two rigid body objects that are based, they are based on these nodes. There's also a ground object that you see on the right. This ground object is having no node because a ground object doesn't have any unknowns. It's just like a fixed entity in space that cannot move, but you can fix or you can attach things to it. In order to connect the rigid bodies, we need markers. So why is it done like that? When I started my research, I also came along to Lisbon. Jorge Ambrosio, you probably know, he's really very famous person. Maybe may I say that even as famous as Aki, yeah? Maybe he's older, I think so. Probably even more famous, yeah. And they were developing also multi-body system software components and so on. And the problem was at that time when I met him that when you connect two bodies, you need to write an interface for them, yeah? And you would connect a rigid body and a rigid body, and you write the interface between two rigid bodies. And then you have a rigid body and a point mass, and you write an interface, and then you have a rigid body and a flexible body, and you write an interface. And this is more or less what we did in our old code, a little bit better than that. But in the new code, I say, okay, we need to have very, very open interfaces so that whenever you create a new object or a new body, then it should have interfaces that are just defined, and everybody who understands the interface can attach to that body. And it sounds easy and simple, but it is not that simple to implement that and to make it efficient, by the way, in the end. Yeah? And so this is done here by the markers. So whenever you can attach a marker to a rigid body or to a body, then the marker provides the interface then to a joint, for example, or to a force. So you can only apply a force via a marker, but you cannot apply the force directly to the body, and that allows us to develop the objects and bodies independently from the other components. Yeah? Okay. Then there is, the loads are attached to the markers, and sensors can measure anything. Sensors are like all the channels that you open to the outside. Here's just, in order to also have equations here, a short glance on the structure of the equations of motion. They are kind of really abbreviated. In the C++ code, they are more complicated. If you look at it, you would never find such structure of equations because they are sampled on the fly, so all the components are computed in separate functions, but more or less the structure is like this, that you have a mass matrix, you have the unknowns Q, that are your mechanical system unknowns like displacements or rotations. Then you have constraints G. The constraints depend on the quantities Q, Q dot, but also on first order differential equations. You have Lagrange multipliers and also time. And this is all combined and solved together as one system of equations. Okay, this is the basic structure. This also brings us then to the solver. This was also, a thing that you have to develop solvers and multiple systems together. That means if you think about developing a simulation code, you cannot just say you take an open source solver, you grab a solver from MKL or any library, but to my understanding, on this level of simulation codes, you have to integrate the two things, yeah? Because they interact heavily with each other. You don't have just a set of equations and then you export the equations to the solver, but they interact. The equations are never written somewhere, but the equations are computed on the fly, and that's why we need to interact between these two entities. And it makes the difference if you are developing a simulation code in MATLAB or in Python, and you are having somewhere the equations of motion, and then you're solving them, and it's usually inefficient, because it would only be efficient if you integrate the two sides to one code. Okay? And here's a sketch of how these solvers work. In the old package that I had, it was like different solvers, and the different solvers were integrated into the whole simulation code environment. And here I tried to split it up a little bit to have solvers, and the solvers should have different functionality, like static and dynamic solvers. And basically, there's always this discontinuous iteration. That means I assume that I have a system of equations with discontinuities. Why discontinuities? It's like contact, friction, plasticity, whatever. Sometimes it's discontinuous. And so you have switches in your system. And you have to get rid of the switches, more or less. Yeah? You say, well, I need to have a decision way or a decision making which state the switches have. Whenever you know that, you can use some more or less Gauss-Seidel iterations for that. When you know the switches, that you have contact or no contact, then you have a smooth problem, and then you can solve it with the Newton method. So the interior that you see here on the right side is that you have a Newton method in the inside. You solve a nonlinear system of equations, and then in the outside you have a discontinuous iteration. We call it then a post-Newton step that is handling the switches. And whenever this discontinuous iteration is converged, then your static or dynamic step is converged. And this is built on all solvers that we have in Exadyne. The whole thing is also extended for Lie group methods. I will not show them here, but they have a very good advantage that when you are dealing with Euler parameters, some people here might have used Euler parameters already, maybe hands up who is using.
You know them. We
Yeah.
discussed them earlier.
But they're also using them, right?
Well, they are aware of what they are, but not so much using.
Okay.
But
But-
we know the whole story back and forth.
Yeah. So the problem is that they are redundant, and that's why you either have to do some tricks about updating Euler parameters, which is very usual, or you switch to.
Euler parameters are redundant.
Sorry?
You say Euler parameters are redundant.
Are redundant? Yes. I mean,
So there's 4 parameters.
yeah, they have algebraic equations behind them, right? So what people very often do is that they say, okay, they are dependent, but let's just integrate them, and the errors are small, and after every integration step you do a projection, but the projection, of course, is not respecting the whole system structure, and you might do some, you might introduce some small errors, yeah? They're not very large, but they would impact the,
Okay,
yeah,
I need
yeah.
to clarify this
Yeah.
because we discussed about the method based on 3 parameters, 4 parameters. 3 parameters, you always have this singularity problem,
Yeah.
regardless how you selecting these 3 parameters. 4 parameters is one way to solve the problem,
Yeah.
but of course it comes with the fact that there's this one constraint because these 4 parameters are not fully independent.
Exactly.
They're dependent. And
Exactly.
that's what you refer to when you explain this story.
Exactly, that's what I mean. And now you have these two sides, singularities or redundancy, and you have to deal with the redundancy.
Okay.
And the point is that we have integrated also the Lie group methods, and what they do basically, they use 3 parameters and they have no singularity. That's interesting because they have 3 parameters without singularities, but you can do the updating, and I can explain if somebody's interested.
We haven't really discussed about this
Yeah.
before.
Yeah, but just to mention, there is now an alternative, and it was also a nice thing to get this done with the code then. And you can look it up how we did it. Okay, there's more specific methods like we're using dense and sparse solvers. We are using Eigen for the solving technology, so for sparse and dense solvers. There's also a full pivot solver. I just found this like a couple of years ago, that Eigen offers a full pivot method. It's kind of hidden in the documentation, and it allows you also to solve for overdetermined and underdetermined systems. They mention it just somewhere in a comment, but it works quite well. And it helps you to also deal with overdetermined and underdetermined multibody systems. What does it mean? If you have a constrained multibody system with redundant constraints, that you have like a joint that, like a revolute joint, and you fix the axial motion, and then you have another joint and it fixes the same axial motion by some reason. Usually you don't do that, but it could happen. And then the solver for overdetermined systems could just resolve that. Yeah? Okay? And then in the end, and this might be interesting for you, whenever you develop such codes, and it can be a small code or a large code, you have parameters. You have to deal with parameters for your simulation engine, and you have to deal with parameters of your system, right? Whenever you're doing something simulation, you have parameters, mass, time integration, whatever.
Let me just take this one thing away because it says that I need to cancel my dentist appointment.
Oh, yeah, yeah.
And
yeah.
I don't think that you guys care so much about that.
Yeah.
Sorry
no,
about that.
the pro- oh, no, that's next thing is popping up. Yeah. So the parameters, you have to get in the parameters. And the question is how you can do that. And you just have to find a way. Here we do it via Python and via structures that we make available to Python, and we interchange. But this is more or less the first thing you have to think about when dealing with simulation codes, how to get parameters in and out. Yeah? It's really, I think, the most important part. Next, the formulations themselves. Yeah. Okay. I will skip more or less this. So then, when you have an open source code, you have to think also where to provide them. You could use GitHub, for example, and I'm always happy about stars. Now I have enough stars that large language models use our platform, our project to train on. Yeah, so they're using our data and they train on, because usually they're looking at the stars, and when you have too few stars, if you have just 30 stars, they will not train on your code, but if you have enough stars, then they train on it, and so that's something that you have to achieve. You can also buy stars, by the way. It's not that difficult. And then you can use some Python platform, PyPy or Conda, where you provide installers, which is very convenient for users to use pip install to install your package, and they will use it much more than without that. The documentation on the other hand side, I found that Read the Docs is quite a powerful documentation engine. GitHub also allows you to have documentation, but nobody uses it, at least what I see. And Read the Docs is providing a very nice way of presenting your documentation. You have to convert it into this form, but it's not only that people can follow your documentation, but it's also advertising your code. Yeah? So if you have documentation on Read the Docs, it's much more visible on search engines than other documentation sources, just to mention it. Okay, so installation is very easy then with pip install, as I said, and Linux sometimes you might need pips 3 install. You can get pre-versions of Exodyne, but I don't want to highlight it too much. If you want to get the GitHub code, you can clone it. Just as a hint, the project is really large. Yeah? It reaches the maximum limits of GitHub, so it's several gigabytes that you have to download. So I recommend just to clone it with dev1, which means you don't download all the dependencies on all the versions. Yeah, it's just to make some sense, and it's much faster then. You can create, you can build it, so you can modify it. It's really simple. You modify the code and you build your own package then using simple build commands. They are all written in the documentation, but just to mention that is not a problem. If you really want to participate in Exodyne, I think this is maybe the issue also here, we don't accept forks on GitHub, but what you can do is just you can send us an email and you want to participate, and we talk about, or we talk here about how to interact, because this is another issue then. Okay, I think I have to speed up a little bit. So the core features are then, we're starting from the nodes, as I said, and this is really, I think, as compared to the old code, it's a quite smooth and how to say, the architecture using nodes and bodies independently gives some headaches. Yeah? ChatGPT doesn't understand it, okay? For example, and it means also students and others do not understand it sometimes because it's not very natural to have a rigid body, but saying the rigid body can only live if you give it a node. In other simulation codes, it would not be the way to go. Many codes, they just have a rigid body, and the rigid body has its own coordinates, and the rigid body can live by itself. In our case, a rigid body needs a node. Yeah? Like a beam needs a node, or a finite element needs a node, so the rigid body also needs a node. This is not my idea, but I think the people in Liège, Olivier Bruls, but also I think Alberto Cardona and all the others, they used that already in their code Meccano. And it's a very systematic way to say, well, you have nodes, one-dimensional nodes, two-dimensional nodes for translation only, or for 2D rigid body, 3D translation means a mass point, 3D rigid body, and so on, or generic coordinates for any flexible bodies. And this can be used then to build upon the nodes more complicated elements. And then you create the rigid bodies out of that, like a 1D mass from a 1D node, and a mass point from a 2D translation or 3D translation, and so on. So this is really smoothly fitting together and extends very naturally also to flexible bodies. And you don't have to do many things again, because if you have a node, a rigid body node, I can already attach a force to the node, and I just build a beam, and I can attach forces to the nodes or constraints to the nodes without any further implementations. It's a very nice hierarchy then. Okay? And then I mentioned already the kinematic tree is then using like a generic coordinates node, and this is a little bit different from structure, but it also fits well into that. Okay. Then connectors. So the terminology I think is a little bit difficult because I didn't find any common terminology to say what are joints and then spring dampers and hydraulic actuators or whatever connects two bodies, two points in space, how to call them in very general. Sometimes you call them connectors, but you also called in different ways in other codes. And these connectors, they start from like one-dimensional connectors connecting two coordinates to three-dimensional or six-dimensional spring dampers. They can include gravity or hydraulics. And then we specifically name the joints that are revolute or spherical joints, for example, that could be connectors. And also contacts are connectors that, then different ways of unilateral interaction of bodies. But they are all connectors connecting two bodies, meaning two markers that are attached to two bodies that are connected then via these connectors. They're very special connectors. For example, a reeving system that you see here on the right, this is connecting several bodies at the same time and putting an elastic line along these several bodies and building up then a model for a rope. Or a cam follower is also a very specific connector. Good. The markers, I think I will skip this, the marker thing. The loads are then the natural extensions of the nodes. So that means that you have one-dimensional forces on coordinates. You can have a three-dimensional force. You can have a torque on rotational coordinates, and so on. This is quite natural then. And in the end, I think it's also for simulation, whenever it gets more complicated, you need to measure things. You need to actuate things, but you also need to measure things. And for measuring, we're using sensors. It's also not a brand new technology, but it's, it's important to define how you can build. I'm sorry for the animations, they just don't work on a MacBook. Yeah, they work on my laptop pretty nicely. But
it depends on what format you use.
Yeah, probably. You need to have sensors, and you can measure either nodes or bodies or markers or loads. There's many different ways to measure in Exodyne, up to the thing that you, for example, have sensor traces where you can follow the sensors in space curves. That helps you sometimes in robotics, for example, for complicated motions. Yeah. Most of the things are then connected with user functions. this is something I didn't know, actually. I even didn't know Python when starting the project, right? This is a little bit of a problem. I knew C++ and I thought, okay, 95% of the code will be in C++, and there is a small Python interface. Right now, when looking at the number of lines of code, it's like 40% in Python and 60% in C++, means it's really a large part in Python. And I had to learn much more about Python. And one thing is, for example, user functions, how to call Python functions in C++. Yeah, how can they even interact? How nice is this done? And that it works, and so on and so forth. And so user functions are integrated. Now I think they have a quite nice way of integration. They are slower than C++ if you have a Python user function. So if you call a Python function from C++ in every time step, that slows down your performance. So you have to think about how to integrate them, but you need them in order to, for example, drive the robot with a certain trajectory. You don't want to program that in C++, but you do that in Python with a user function where you provide the trajectory in every time step, and this is done by callbacks or user functions. One of them is the pre-step use. That in every step you can call a user function, for example, that does it. Or you can just make a constraint or a spring damper with a user function where you can implement any material model that you like. User functions, I also like this slide. We also implemented the floating frame of reference formulation, and I don't want to go into any detail about it, but it should just say that the possibility to connect Python user functions with C++ allows us to implement very complicated formulas, and doing that in C++ is really a nightmare. Yeah, I did that, but in the old code we had 4 people implementing the floating frame of reference formulation, and guess how many different solutions we got? Yeah, and it was really 4 different solutions. Yeah, and synchronizing them, I think we got 3 of them doing the same. 1 we just threw away. So it means 4 people were doing that, yeah, 1 lost, okay? And the other 3, they agreed in the end. That was 15 years ago. And it was very hard because it was done in C++. Doing that in Python is like an afternoon, yeah? You can implement that formulation in an afternoon in a user function, and it looks like what you see here below. It's not looking nicely, but it's just using NumPy, and it's immediately working, yeah? Immediately, without any problems. And then you can put it into C++. And this is what you can think about how to implement things if you have complicated formulas. But no more about that. Let's see. Now, to connect C++ and Python, you need to have a technology to combine the 2 worlds. Yeah? And I think this is the core of everything. It's not very complicated. There's a couple of ways to do that, Swig and C-types, and we use PyBind. Why PyBind? Because we evaluated the different ways to do it, and PyBind turned out to be very good 7 or 8 years ago. Now, you never know, will it be still good in 10 years? Will the project continue in 10 years? You don't know. It's an open source project, but it's done by people that are amazingly well performing and keeping the project and further developing the project. So it was a good luck to use that PyBind, and I can recommend it for you as well. Now, PyBind is not very easy. The easiest example is shown here on the right. If you have a C++ function for adding 2 numbers, you just need to write a little bit of C++ code, and then you can implement, or you can import that function into Python more or less. It's very, very easy. Nowadays, and this is really a big change, all the AI models can do that for you, and they can really do that precisely. And they know all the tricks behind it, and you don't have to do that manually. When I started the project, I did that manually, and it was almost a nightmare to get this running because PyBind can give you a lot of errors. Nowadays, I would say it's no problem. Everybody can do it. Yeah? You have a Python code, and you say, well, the Python code is slow. I want to export some of the part of the code to C++. AI can help you to do that. Okay? So it semi-automatically links to C++. It also includes some documentation. There's a small overhead. It directly integrates NumPy to C++, and it makes a lot of things possible. There's only, what we do is, we don't write the PyBind code by hand because it's very, how to say, it's heavily templated code. It's an own language, more or less. And as I said, AI knows how to work with it. If you forget any like semicolon or anything here, if you do something wrong, it will maybe compile, but it will not work, yeah? Because it's a heavily templated meta language. It's really a nightmare to work with it from the scratch. That's why I avoid writing that by hand, but we are generating the connecting code more or less. Yeah? So we are using just a few features of connection, and that's then generated automatically in order to avoid all the coding issues that you would have if you do it manually. That's just a thing that I want to say. Okay. But important thing is that we now, due to the interface, for example, any modeling or even eigenvalues, optimization, whatever, everything is done in Python, and it's really separated between C++ and Python. And some C++ methods even call Python. That's also possible, that if I need a singular value decomposition in C++, then I can make a Python call from that. Okay. Yeah, here is just a slide that again highlights that we're doing a lot of automatic code generation. I would not have shown such a slide 10 years earlier. 10 years ago, automatic code generation was really, how to say, people said this is bad way to do, bad habit, yeah? Don't do automatic code generation. There are other ways to do that, yeah? You should avoid that. And then I read that Google and many others do that again because it's a way to overcome code duplication. It's just a systematic approach. It makes your life easier. And it's just shown here that in our code, we have now like 90 different markers, bodies, nodes, whatever. They have more than 700 parameters. And these parameters occur like 17 times everywhere in documentation, interfaces, and other places. And I would have to track all these more than 10,000 occurrences, and I don't have that much time. I have much time in the night, but not that much time. And that means that you need to do automatic code generation if you deal with that. Yeah. Okay, I have to speed up a little bit to come to the Python extensions. In the old code, we also noticed even when you start with a rigid body, then you sometimes have to think about how to compute the inertia, right? Inertia for simple shaped bodies. And so this is something that I would like to have a supporting tool in Python that helps you to compute the inertia for simple cylindrical or other shapes, so that you don't have to compute that formulas always by hand. It would make your code very long. Or if you import a mesh, a STL mesh, then it should just allow you to compute the inertia directly. The same thing for graphics. So you see these nice graphics. How is it done? It's done by Python utility functions that generate a gear or a chain or whatever, and this is just imported, and you don't have to think about how to import that from a CAD tool or whatever, because you have a chain that always changes the dimensions, and you will always have to draw it again. This is not what we are doing. So this is all done in utility functions, even for post-processing or particles. We use matplotlib for post-processing with some interface to Exodyne that makes the simulation output easier. The same thing, I think this is also very practical for research. Whenever you do a simulation, you don't want to do a simulation actually, right? I mean, we are doing simulation, but why do we do simulation? Who in industry needs a simulation? Nobody, right? They want to have a solution. They like to solve a problem. They want to know which parameters should I use, how long should I make a boom, or which material should I use? Yeah, how thick should it be made? But you don't want to say, oh, I want to have 10 simulations. No, no simulation, right? So what you immediately need after you can simulate something, you want to do optimization or parameter variation, right? And this is something that we integrated as well in Python, that you can do parameter variation. For example, here you have a deflection over a frequency, and you just change the frequency, excitation frequency, and you compute the deflection with many different simulations. You can parallelize it, by the way. So nowadays, on a supercomputer, can do a couple of hundred simulations at the same time, and you can more or less do all the variations at once. Yeah? And even on a local workstation, it works nicely. Also for optimization, very often you say, okay, I have to choose a parameter, and therefore we have integrated this genetic optimization that then nicely interacts with the core code, and it is parallelized. That means whenever you do a genetic optimization, you have to compute the population of maybe 100 different parameter sets. So I'm not sure if this is optimization is known here already, but optimization, there are many ways to deal with it, very sophisticated methods. But for complicated systems, sometimes they break down to like genetic optimization or nail-the-meat method. And there, you have to compute the simulation with many different parameters at the same time. For example, in genetic optimization, you compute populations, and in every population, you compute 100 or 500 or even 1,000 simulations. And from that results that are shown here more or less in the blue dots on the right, from that results, you think about where to go in the next population. Yeah, it's like a genetic approach. And these 100 simulations, you can parallelize these simulations on a good computer, even on Macintosh, or you can do it in a supercomputer, and it speeds up that thing. Okay. And what we also integrated via Python is like eigenmode computation. Like for this system here, you see it's a typical special mechanism that our kinematics experts like. It is a system that should not be able to move, but it can move because it has redundant constraints, and you can compute just the eigenmodes for such a system by using classical eigenvalue analysis that is integrated here as well. I will skip the beams, but for the finite elements, then we use, this is also an advantage of Python. There are many packages available, and the question is how you can integrate them. And for example, for the finite elements, we use ngSolve and NetGen that can be used to generate meshes. ngSolve is also a very nice Python package, and you can combine it with Exodyne. We write just some interfaces to import the mesh and even the matrices, the stiffness matrices and so on, and can directly compute the modal reduction with ngSolve. There's also some interfaces to robotics and AI, so we can import robotics models from the robotics toolbox. There's a robotics toolbox, was in MATLAB. I'm not sure if somebody was using that. It's from Peter Korke. It's very established, more than 10 years. There's a book about it. And he started with a very simple package in MATLAB, but now extended that to Python. And there's a lot of robots, for example, available there, like the Spot is just taken from there, but you have a couple of dozens of robots that you can import there, and this is where we get our robotic models. And they're described with this URDF file. There's also an interface to ROS, to the robotics operating system. And with that, we can then, for example, use AI to train to train such robots. They're not perfectly working because it's always about the reward. In this case, the reward was that the feet get very close to the goal, and if the feet should be close to the goal, then it would stand in a very special way there in the goal, as you can see maybe. We also wanted it to jump on a box, and the robots don't want to jump, by the way. So we said, well, you get a reward if your feet are high. So then it said, okay, then I'm just walking on 2 legs because then my feet are very high. And in the end, it did it. We just didn't include the contact for the one link, so therefore it learned a very special behavior, but it could jump on a box. It was by the way, a student project last semester to be done like that. Okay, yeah, there's also visualization. Why did we improve the visualization? Visualization is a big nightmare again. I think it helps you a lot, and it's like the solver. If you have a multi-body tool, if you don't have an integrated visualization, you would never know what you simulate. That's a big issue. Sometimes you make errors because you just don't see them. And then when you see what you simulate, then you find out that like there's the robot, maybe you can see it, is touching the ground here on the right side, yeah? Which means that you immediately detect some errors, yeah? You don't need a sophisticated simulation or visualization engine, of course. And the point is now, why did we extend this visualization recently? Because we are going to AI. I'm not talking about here directly, but we are also using images. So we need to get out images from our simulation, and in order to do so, we use some kind of ray tracing, as is used here, that can be done offline. You don't need to start any window, but it's just in the background, grabbing the image of your current scene, and then you can just use this image again for AI. And I think this is a very important feature that you need to have an integrated visualization for training your AI. But otherwise, you can use it to view your solution or creating animations, which is very important for me, because otherwise I wouldn't have any animation if it wouldn't be very, very easy. Yeah? It's really, like in a minute you can create an animation. I hope you agree with that. It has even now the button to make MP4 animations integrated now. Okay, I'm not sure, still some time, maybe a few minutes. Now I would just jump into a real model, and we would do that interactively, but I think this is not possible right now here. I just still want to show you how it is to create a model in Exodyne. And due to the redundant structure of the systems, it is quite straightforward. You don't have to know a lot. It's like a language that you write in a Python code to create a multi-body model. And you start with it in a very standard way that you import libraries. You import Exodyne, utilities, graphics, and NumPy probably. And then you create the multi-body system, which is one of several systems that you can create. You can create more than one system at once. And then you, of course, usually have your parameters, but then you just create objects. This is a simplified way of dealing with the Exodyne interface. So we have the core interface in Python, and we have simplified functions. Why do we have them? Because we saw that it's much easier to work with them by ourselves. The students like it a lot, I noticed, and AI likes it a lot. AI couldn't deal with the core functionality. It was too difficult, but with the simplified functionality, it was easier then. Yeah? And for example, if you want to create a rigid body, then you see here, we first create the inertia, like here it's for a brick-shaped object. We create the inertia. We can even, we can make some translations of the inertia. And then we also create some graphics to make the visualization possible. We don't need it, but it's very helpful. And then we create the rigid body from the inertia, from the graphics. We add some gravity reference position, could also add initial velocity and other things. And then we create just one rigid body. The rigid body gets a number or an index, and this number can then be used to connect the rigid body to other bodies. Yeah? For example, if we create a revolute joint, then we connect the revolute joint, or the revolute joint connects the ground object that we created before and the body at a certain position with an axis, and then you just have a revolute joint. It's not more than that, yeah? Even including a visualization, a basic one. And this is only possible due to the redundant structure, because in a minimal coordinates formulation would be much more complicated to define your mechanism by serial or tree-structured kinematics. Okay. So why using redundant multi-body systems? It's not always the most efficient way to deal with it, but it can also be very easily extended to parallelization. And whenever you want to speed up your simulations, you could look at Exodyne, how it is done, because this is something that maybe is done in very professional simulation engines, but in most codes you don't see parallelization because multi-body dynamics is not suitable for parallelization. Yeah? And in Exodyne, due to this redundant structure and by design, we wanted to have a multi-threaded parallelization. And the important thing is that it uses an own very fine granular task scheduling with also load balancing, but task scheduling with very small overhead. And this is required to parallelize any computation of mass or forces and whatsoever in parallel, because they're all very small tasks, and parallelization usually likes to have big tasks or 100,000s of objects of the same structure, but we have 100 forces, 100 springs, 100 bodies, 100 whatever. So it means we don't have these 100,000s of particles, then it's easy, but we usually have, like here the robots, it's not the best example, but having like 100 robots, but it's not very much, yeah? Can we parallelize them? And it's already efficient. If you have only 2 robots, we can already benefit from parallelization. And it's very few code that's just by design. And you can look at the task scheduling. It's a simple library. You can also use it for other projects if you like. It's built, by the way, upon ngSolve's task manager that was doing that 15 years ago, approximately, for finite elements. Yeah, I must say. Here's an example for parallelization that is like a simple belt drive, and it has 480 beam elements. So it's a very small system, but parallelization works there already nicely and gives us a speed up of 3. It's not very much, yeah. But the point is, 3 hours or 1 hour is a big issue, and that's why parallelization just helps. The same for particles, just kept here. We use 64 cores, we get a speed up of 13. It's not dramatic performance increase, but factor 13, I mean, would you take it if you get it? Yes, yeah. Because 13 days, 1 day, yes, it's important. But it's not highly efficient. Why? Because not all parts can be parallelized. Yeah? Some parts of the solvers are impossible to parallelize, and that's why there's some gap left. Okay, just some applications. We were dealing with steel, with lawnmowers mostly. It was a very basic project in the beginning. We also had a simulation with our rope way manufacturers, where we mostly modeled the rope with 2-dimensional, because it's everything in 1 dimension. There's just the 2 wheels, they are actually in another dimension, but it doesn't matter if you just change the orientation of them. You get the overall dynamics of the rope system anyway. Yeah, then just examples. This was a work together with people from here that we did the reinforcement learning. I just want to skip it, but it was a nice application of Exodyne. And we also worked now on surrogate models that should allow us to actually replace simulation by using machine learning to learn the behavior of the robot and to predict the motion or some components of the simulation by machine learning models. And this nicely works where we can just, instead of simulation and having a couple of seconds of simulation, we can just predict some components, and this gives us then a speed up of more than 1 million, which is quite nice if you have very time-consuming simulations. Yeah, this is more or less, I think I came quite well through it with the time. This was more or less an overview. I hope that something was new for you, or that you get an kind of impression how it works like, and maybe it helps you for your own projects. Just some future plans or recent developments. We also now again implemented a plate element with some extensions for pre-curved elements that is ongoing for a project with people from China. we had many of these create functions to simplify the, the code interface. As I said, we have this offline rendering for the AI tools that we need, and we also added doc strings that help a lot to work with it. So doc strings are in Python a way to have an integrated documentation, and whenever you type a function, then it will tell you what the function does and what are the interfaces and so on. And this was already integrated earlier, but now we have it, I would say, fully integrated. And there's still a lot to do. Three-dimensional beams are still not there where they should be. C++ user functions are still not possible. I mean, it would be possible by doing it yourself, but they are not integrated. And like adaptive step size is planned for generalized alpha, some advanced contact formulations. But this is more or less it. Question maybe in the end, what would you expect? What are your needs or questions? What would you like to have? Maybe a couple of minutes of questions is possible, even with YouTube. Maybe people in YouTube can just write it in the channel, and Aki will read it. And if you have some questions, we can answer it right now, before we then switch to, I think, your announcements for the exam, right?
Yep,
Yeah.
exactly.
Okay.
So my question is, what about real time? So if I would like to run everything in real time, because that's of course helps you to make your simulation model to be used in other product positive and product development, like embedded solutions and such, so like any parts in that regard.
That's a good question. I mean, the question is first, is real time or real time? So we had some requirement.
Real time, I mean real time, the one that you mentioned first, soft real time, not the hard time.
Okay, soft real time is basically possible. You can turn off all graphics. You can even compile the software without graphics, that it runs on a very small microcontroller. The question is, of course, how to get your models running. If you wouldn't have Python, then you would have to set it up in C++. That's not intended to be done, but it is possible to be done. And there would be, probably we would need a way to get the models integrated. That's maybe the biggest issue. But regarding the solvers and everything, real time is not a big problem. Yeah?
You still need to, I think you're solving things faster than real time, I believe so.
It depends
So
on the
you need to
model.
slow down, so you need to wait until that time hits the, so you still need to synchronization.
Sure. I mean, as it is done with, so from Python side, there's all the synchronization possibilities. Like in robotics, in ROS, we can do real time. We are doing that, by the way, even. But if you have other machines, like hydraulic mechanisms, or then you might not be willing to have Python there, and then it's more difficult. Because in robotics, you always have Python. Yeah? You would even run ROS and everything in the loop. With ROS 2, it's all possible. And there's also a real-time mode where you can run the simulation in real time, but I think what you are aiming at is to put it on a microcontroller somewhere, right? And then there is some way to go, but it's not impossible. And the speed, of course, would be possible, yes. So, yeah. Okay, any other questions?
Yeah, one question.
Yeah, yeah.
Is it possible to import your 3D models to this?
The question is how you can import it. I mean, the question is first, flexible or rigid?
Let's say rigid.
Yeah, because rigid, the first way to go is always STL, because then you would have, if you have a STL geometry, you can always import it. It's more or less the graphics, because you just need the inertia parameters, right? Everything else doesn't matter. There are other ways now. They are just, I mean, you can always use any Python package to import everything. So this is also a way that you just maybe need a translator to get to STL finally, but you just use any Python tool to do that. That's some people doing. And we now integrated in the current version with PyMeshLab, you can get many different formats. NotStep, for example. For that, you need meshing that you can do with NetGen again, that we're using for the flexible bodies as well. And so for the flexible bodies, then with NetGen, we can import 3D models. We can also import ANSYS or Abaqus models, but you have to have the interfaces more or less to that. Yeah, they are prepared. They work for some cases out of the box. It could be possible that you need to change something in the interface. Yeah, but it's all on a Python level, so it's something that if it doesn't work, you give the code to AI, and sometimes it even would give you nowadays the extension to the case that you need. Yeah, and of course with care, but and with okay. Any other questions?
I have a question. Is there considered an executable build of the script so it would be not dependent on the Python or C++ environment?
That's a good question, hard question. I removed that. Oh no, export symbolic system equations. It is a plan, and I think it would have been. I'm not sure if I should repeat the question here for the YouTube.
Yeah, please
guys.
do that
Yeah.
because the online participants may not be able to hear
Yeah.
because the mic is a little far off.
Yeah, so the question is if we can export an executable of the model somehow so to work without Exodyne and Python maybe even, and that's just basically right now not possible. But if we wouldn't work on AI and all these things right now, which gives us many attractive opportunities, then the plan was to export symbolic system equations. So everything is prepared, but it's not realized, and it's it has to be done with the full code to export symbolic equations, recording of equations more or less, and this would what we would do to export the model in any form that you would need then. Yeah? I'm not sure if this answers, but this is the way that is planned, but it's not yet realized. Do you mean something
So
different?
it's,
Yeah.
for now, it's closed in the environment you are solving this. So you need to install some kind of C++ or Python environment and work only in there.
No, you just need to have Python. You have Python and you pip install the build. For that, you don't have to do anything else. Yeah? You just need the Python model. But of course, if you say, I want to now transfer it again for real-time systems to a controller, then the symbolic equations would be the way to go. It would be also very efficient. Not symbolic, it's a kind of symbolic representation of the model as a mathematical expression. Yeah? Okay?
All right, guys, are you happy?
Yes.
Okay, very good. So let's give a big hand.
Thank you.
Very good, very good. Now what
Bye-bye.
follows is that I'm going to take over your mics and everything.
Oh.
And those ones that are representing our lab and the others that are employed by LUT. Where was this? Oh yeah, there it is. Are dismissed. So you guys can go. Okay. Because we're going to discuss a little bit something that is not your concern at all. So it's going to take 20 minutes. 20 minutes. Okay. Here, before we're moving on, so I want to mention this. Remember when I mentioned about me losing my mental health? That was related to this played element in ANCF, the one that is mentioned in the very top of the list. That was the one that was this 48 times 48 matrix when I tried to build these shape functions, and I'm never going to forget the number 48. Okay, guys, you're dismissed. So see you next time. Thanks, guys. Hey, and I would like to mention, this is already the class members. Multiple times in Johannes' presentation was mentioned about AI. So what follows is that we're going to have the skiing break, the winter holiday break. That's going to be next week. A week following that will be 4 weeks in a row. There's going to be AI seminars. Sebastian, that one that is standing here, and Greg are the ones that will handle this AI workshop. And if it would be up to me, I would make this AI workshop to be mandatory for all the master level students, because this is the kind of skills that really makes sense to you to master. It's a little bit about the large language models, but it's about the surrogates, about, Sebastian, tell me what it's about. Reinforcement learning, okay, that's a fantastic topic. And what else?
And large language models.
Large language models, all right?
So three main topics.
Three main topics. So surrogates, large language models, reinforcement learning. Each of them are extremely important matters to learn. So, and you're going to learn it by hands-on way, so you're going to do something by yourself.
Exactly.
Another thing that is good to mention that exam will be available in a week. So let me take a look at my calendar. So the weeks that are week 9, 10, 11, and 12. Those are the weeks that you can select the exam time, whatever way you want. Okay, what's up with the exam? So let me then explain that to you. So just a second. I'm gonna be brief here so we can go and make a visit in our laboratory. So we're gonna discuss about this stuff. So recap, just need to check like if how I'm displaying in a YouTube. Here, live. So it's looking pretty good. Okay, now here are the rules. So these are all the questions that may be in your exam paper. And as we agreed earlier, so the rules goes as follows. So I have some 20 something questions, and there's going to be voting actions that will be taking place later this week. And in these voting actions, you can vote one question that will not be in an exam paper. If there's a paper that you hate a lot, and this is of course democracy. So you can just cast your vote, and then based on your democracy, we're going to take one question off the list. And we'll let you know that later once the voting action is closed. And the voting action will be on sometimes maybe tomorrow, on Wednesday at latest, and then the results will be announced to you on Friday. So this is going to be one question that you should not focusing on. And then another thing that you should focusing on, there's going to be one question that will be in an exam paper for 100% certainty. So 2 items that we can ask from you. What's the question you hate the most? What's the question that you love the most? And based on your voting actions, we're gonna put one question in an exam paper, and we will take one question away from this list. Also, something that I did yesterday, I was using the Notebook LM, and I make actually 2 podcasts in Finnish, and I said in Notebook LM that make the podcast in a way that you answer each one of these questions. I did not listen to this podcast by myself, but if you wanted to use it, that's okay. But it's your responsibility, because I have not checked if it is correct or incorrect. And I also wanted to do the same in English, and I did the first one, but then I went out of my quota. So it just said that I have no rights to make many more podcasts. So that's why there's only 1 podcast in English, 2 in Finnish. Sorry about that. Maybe I should subscribe the commercial version of Notebook LM. But anyways, I'm sure that international students are clever enough so you can manage with the 1 podcast only. And again, no guarantees about the quality. No guarantees. All right? So these are the questions. So be prepared to see some of them in exam paper. There's going to be a total of 5 questions. One of them is already something that you are aware of, and 2 of them are a little bit of surprises. You guys will have an access to this PowerPoint presentation, so no need to take a pictures. Okay, so many things we already know. There's a little bit of summary about each of the topics. This story continues. Some of them are a little difficult, but I figure each one of them are covered in our lectures and in the podcast. Okay? Then even if questions are in English, please, the podcasts are in Finnish, please enter your answers in English, because we're going to use my research team to grade you, and some of them are not able to communicate in Finnish. So English answers only. All right. 3D kinematics, I'm going to be very brief here. So we discuss about the way the particles can be described in spatial cases. And we learned that the rotations is one of the headache here. And the one way to do that is that we can use 3 rotational parameters, like in the case of Euler angles. Concept that is based on successive rotations. Or we can use Rönnquist equations, or something that is close to that, like Euler parameters. So we learned from Johannes' presentation that the Euler parameters consist of 4 parameters, but they are not independent. There's one constraint equation that combines them together. But this constraint equation comes from the fact that in Rönnquist equation there is this unit vector v, unit in a length, and that's where the constraint is coming from originally. And that's a physical interpretation considering those constraints. mathematical properties of rotation matrix. We did not discuss so much about that, but for your information that the rotation sequence order makes a big difference in the spatial applications. Comparison of different method. Please be prepared to see a question where we're asking about what's the difference between the Euler angles and Euler parameters. And then you need to answer based on how many parameters are involved, what is the usability, what about the singularity, what about the constraints, and so on and so forth. Something we discussed earlier. We also discussed about this robot kinematics that is still kind of based on multi-body system dynamics, but tailor-made for robotics applications. And it helps you to create robot kinematics like almost just like that. Then one of the methods that is heavily used was Dynamit-Hartenberg, based on 4 parameters. Each of them, let me see if I can use my pen here. This guy. Oh, not connected. All right, I'm not going to use my pen. I can use it here. Yep. Let me take myself back. This is where we started. You know, these 4 parameters are visible, not clearly, but they're kind of visible in this figure. And these parameters are length, angle, another length, like how much they are off from 2 bodies of each other, and an angle again. And the way you can build the kinematics was creating this kind of table or matrix, and then you just put the numbers of each of these 4 parameters. And that's going to be the one thing all you need to create the kinematics for your robotic system. So it's pretty straightforward. And that's why that it is fairly often used in a robotics applications. Okay, so then moving forward, this was the complicated matter. So this was something we discussed. And this is something that is medium importance. Look at again, each of the subject matters are rated by a star, referring how important it is to learn it. So we discussed that in 3-dimensional space, angular velocity vector is not the same than time derivatives of rotational parameters. You can relate them, and you can relate them by using this famous matrix G. So that's the way to connect them together. I would say that if you're busy, forget about this subject matter because it's not likely that you can see that in an exam paper. But other matters, acceleration was something that was fairly straightforward. Maybe it makes sense to you to be familiar with that. And then a few questions about flexible bodies, when their deformation needs to be accounted, and there are cases when the accuracy needs or requires deformation to be accounted. You know, what's the case about the linear strain displacement relationship, how is affecting this famous example we look at, and that was a cantilever beam, and explain the concept of lamp mass approach. That's another one. Lamp mass approach was something that you take your original body and you divide your original body to multiple rigid bodies, each of them connected by a spring element, and the spring elements have a degrees of freedom in all 6 degrees of freedom in a spatial case. And this is something that still kind of falls in a category of rigid multi-body system dynamics because formulation is not being changed. And then we discussed about the floating frame reference formulation, the general idea. This is very, very important. Please be aware of that. Please understand what that is coming from. Please be able to compare different methods, which is lamp mass, floating frame reference formulation. We discussed about that lamp mass is mainly for beam-like bodies and is not very sophisticated method. Is like quick and dirty, if you want to use that phrase. Floating frame reference formulation is something that is computationally way more efficient, way more accurate. And these are the last questions. We discussed a little bit about the basics of finite-element method. You know, how is that the polynomials can be used to create the shape functions? How is the Pascal's triangle related to that? Convergency rate was something we discussed too. And the last set of questions is like, what is that the shape functions are describing? Physical interpretation of eigenvectors and eigenvalues, how to conduct an eigenvalue analysis in general, and mass normalization of eigenvectors. Each of them again discussed. This was something that you can take your polynomial expansion, and with help of the kinematics, you can convert that to be a safe functions. Safe functions are telling you that how the particles within the boundaries of the element is assumed to behave. So it's like soul of the element. And in the beam element, we learned that they look like this. And again, depending on what kind of polynomial expansion you use, you can play with the safe functions. And that's kind of like the core of displacement-based finite element modeling. And then this, of course, is solution procedure that you can solve the equation motion directly, or you can first move in the model space. With help of model reduction technique, you can achieve quite a bit of efficiency in your computing. This is something that model reduction is highly rated. So if you look at the number of stars, quite a bit of them. So it makes sense you know that. And how you can reduce the size of your original problem with help of model coordinates, that's something that is extremely important. So with that, one more, this was our final questions, and 23 questions in total. The last one was something that is quite nice, where the word floating is coming in a floating frame reference formulation. Remember, this is the way you describe in your deformation modes, and when it is possible that reference coordinate system is not attached any of the material point, and that's when the reference coordinate system is it is traveling and rotating, but if body is deforming, then it's floating with the body. And that's where the name floating is coming from, floating frame reference formulation. So with that, that's all for now. And like mentioned, there's going to be further instructions available a little later about the questions, and the voting action will take place a little later. So please cast your vote, because it makes a difference. It can make a difference. And then we continue on, let me see, I think it was 2nd of March. Let me take a look at my calendar. That is 2nd of March. And Sebastian and Craig, I believe that these AI workshops are organized online, entirely online. Entirely online. But your participation is needed. So if not capable to participate, let me know in advance. Because those are the kind of the workshop that once they get in started, it's hard to jump in later. So try not to skip any of the classes. Yes, Craig?
Yeah, just a short note that the first one, correct me if I'm wrong here, but the first in the series will be just the lecture.
Okay, okay.
So then it won't require anything, plus maybe like advices about the setting up the system for you to work.
Okay.
And the following 3 will be
All right.
about active participation.
Okay.
And
All right.
maybe we should also.
Okay, Craig, hold on, because I need to repeat that to online participants. So the first one is going to be a lecture that is going to be available over the YouTube, I believe. So you guys can have my streaming key if you behave in responsible manner. And then the first one is about the lecture, a little bit about the background, about the matters we discussed. And then also the instructions how you can prepare your computers and other tools ready for follow-up seminars. So the first one is a lecture, and then 3 others are hands-on workshops. Go ahead.
Yeah, and I would like to emphasize that, okay, we also, after each of those workshops, you are requested to do some job, and the way that you are presenting your results is by sending maximum 2-minute video.
Oh my God.
describing, Like, is it 2 minutes?
2 minutes.
2 minutes, yes.
Yeah, makes sense.
This kind of pitch-like presentation of what you've learned from this workshop.
Very nice, super nice. Okay, so I'm gonna repeat this again. So after each week, there is a homework or assignment that Greg and Sebastian are expecting you guys to finalize. And you need to submit your results by making a 2 minutes video. Is it each of them need to do it individually or teamwork?
So can you help me? And I just want to emphasize that, will be also Jakob is also involved.
Okay, Jacob is also involved.
Yeah.
So it's a three teachers that are involved.
Well, mostly the young guys. I will be just
Okay,
in the shade.
so there's going to be supervisor Greg and the heavy lifters. That's going to be Sebastian and Jacob.
Exactly.
So the actual work will be conducted by Sebastian and Jacob.
Yeah, this is
And if
my-
everything, and if there's any, if it goes fantastic, then all the credits goes to Greg.
Exactly.
And if there's gonna be failures, it's all about Sebastian and Jacob.
Yeah.
They made a mistake.
That's the business.
Yeah. Yeah, because Greg knows it so well because he's a professor already, so he knows like when to put like complete radio science and whenever to collect the credits.
Yeah, I know when to show off.
Yeah, exactly. Whatever smells like a victory, it's gonna be all about Greg. Good thing. Okay, so that's what follows, and I think it is gonna be something that you guys gonna enjoy a lot. Extremely important subject matter because we learned that AI is making a big difference. Another day, like you guys too, I believe you are reading the Helsinki Sanomat. So there was a news about one of the consulting companies at the plant will let people to go, engineers to go, because they're gonna replace those engineers by AI. So my interpretation is that it's hard to replace engineers completely by AI, but those engineers that are capable to use AI will replace engineers that are not capable to use it. So you need to make sure that you can use it. So that's something that is like insurance, whenever you are gonna be somewhere out there. Okay, with that, exactly on time, so we go and have a lunch. You guys go wherever you want. I'm gonna close the streaming and see you guys next time. Good.